In this video, we are going to do outlier detection and removal. Outliers are the data points which are data errors, or sometimes they're not data errors, but they just represent the extreme variation in your data set. So although they are valid, it makes sense to remove them. Otherwise, they can create some issues later on. We can apply now different techniques to detect the outliers and remove them. And these techniques are you either use like standard deviation, for example, or you can use simple domain knowledge. One of the things in real estate domain is that when you have, let's say, 2-bedroom apartment, it cannot be 500 square feet in total area, right? Usually, see, look at all these guys, right? Like here is 1056 square foot, but it's 2 BHK. So if you just divide this by 2 BHK, you get like 500, for example, okay? Here also 2600 you divide by 4 and you get around 600 to 700. So we want to first look at any data rows where the square foot per bedroom is less than some threshold, okay? So as a data scientist, now you go to your business manager who is a real estate expert and you ask him this question: what is a typical square foot per bedroom, okay? And he will tell you that it is around 300. So if you have any case, for example, you have, let's say you have 600 square foot home and the total number of beds bedrooms are 6, then it means it's 100 bigger location. And when I do that, what I find is this scatter plot. 3-bedroom apartment, this is green is 3, has higher value than 2. I mean, I still have removed how many properties I have in per square foot area, okay? So when I run this code, what I find is majority of the properties. So here on the x-axis, I have the unique values here, and you can see that there are properties which has even like 1,000 home, and I do have the histogram here. Now I'm having 7 bathrooms. So that I have to drop some CV to come up with the best model. In last tutorial, we cleaned up our data frame and made it ready for model building. In this tutorial, we are going to build a machine learning model and then use k-fold cross-validation and grid search CV to come up with the best algorithm as well as the best parameters. Here in this data frame, we have a location, and as you all know that machine learning model cannot interpret text data. This one is a text column. So we have to convert this into a numeric column. And one of the ways of converting text column, which is a categorical information, into numerical information is to use one-hot encoding. It is also called dummies. So we are going to use pandas dummies method here. And the way you do that is you take your data frame and the column that you want to hot encode, and then call pd.getDummies function on it. When you run it, what it will do is for each of the locations, it will create a new column. So for example, first few locations are first block Jayanagar. For that, create a new column and set the value to 1, and remaining all the values are 0. When you have a location as first phase JP Nagar, the value, see here, the value is 1 and remaining values are 0. So it is a pretty straightforward encoding method. If you want to know more about this, I have a separate video just to cover one hot encoding. Now let's say you have these dummy columns here, and I'm going to store them into a separate data frame. So it looks something like this. And then I will append that into my main data frame. So I'll create a new data frame called df11, and I will concatenate df10 and these dummies, okay? So df10, so the way you do that is df.concat, okay? I want to concat 2 data frames, df1 and df2, on columns. All right, now which are the 2 data frames that I want to concat? One is df10, the second one is dummies. All right, now we learned in our other one hot encoding tutorial that to avoid a dummy variable trap, you should have one less dummies column. Let's say if we drop first block Jayanagar column, then to represent this column, we can use zeros in all other columns, and that will mean it's first block Jayanagar. So we can live with one less column, and for that reason, I'm going to drop the last column here, and the last column is other. So this is the column I'm going to drop. So this column. Then to represent this column, we can use zeros in all other columns, and that will mean it's first block Jayanagar. Drop first block Jayanagar column. Then to represent this column, we can use zeros in all other columns, and that will mean it's first. All right. Now we learned in our other one hot encoding tutorial that to avoid a dummy variable trap, you should have one less dummies column. Let's say if we drop, and now my data frame looks something like this. So it has our necessary features such as total square foot, bars, price, etc. And then all the location columns are dummy encoded. Okay, so they are represented as numbers. So of course now I can drop this location column because I have already covered that column into those dummies columns. So here I will just drop that column and create a new data frame, call it df12. Wow, we are already at number 12. So this shows how long our data processing pipeline has become. This is like a pipeline. df1 is one stage, df2 is second stage, and df12 is probably the 12th stage. We are now all set to start building our model. First, let me examine the shape of the data frame. So we still have 7,000 rows, 245 columns. I will create an x variable because x variable should contain only independent variables. Okay, my dependent variable is price, so I need to have price drop from my data frame. So I will say drop the price on x is equal to columns, which means drop the price column, and that will give me my x, which I need for my model training. Okay, so x is all independent variables, total square foot, bath, BHK, and remaining all the columns are representing the location. And y is df12.price. Okay, and when you do y.head, right, so my x and y are ready. Now you all know from my other train test split tutorial that we always divide our dataset into training and test dataset. Then we use training dataset for the model training, and to evaluate the model performance, we use the test dataset. Okay, so we are going to import train test split method from sklearn model selection, and my test size is 0.2, which means I want 20% of my samples to be test samples, and remaining 80% I'm going to use for model training. Now here what I have done is I've created a linear regression model. I have a separate tutorial on linear regression, so if you want to look into the math behind it, you can follow that tutorial. For this tutorial, we're just going to call fit method on x train and y train, and once the model is trained, which is in this tab, the next step is to evaluate the score of our model, which will tell you how good our model is. When you execute this, it will do the training on x train and y train, and then it is giving me the score. So the score is 84%, which is pretty decent. Typically, a data scientist would try a couple of models with a couple of different parameters to come up with the best optimal model. Okay, so that's what we're going to do. We're going to first use a k-fold cross-validation. Again, for k-fold cross-validation, I have a separate tutorial. So if you have any curiosity in knowing the details, you can go and watch that tutorial. Okay, so here I have imported some needed methods, and then I'm creating a shuffle split for my cross-validation. Shuffle split will randomize my samples so that each of the fold have equal distribution of my data samples, so it's not just targeted into one area. Okay, and when I use cross validation, I'm getting these scores. So you can see I'm kind of getting more than 80% score all the time. I mean, here I got 77%, but majority of the time I am getting more than 80%. Okay, I don't want to go into detail of how cross val score works because that's a big topic, and if you don't know about that, I recommend that you watch my k-fold cross validation tutorial. Now next step is we figured that for linear regression, even if you run 5-fold cross validation, we are getting score more than 80%. But how about trying few other regression techniques? Okay, there are like lasso regression, there is decision tree regression, there are various regression algorithms available. So as a data scientist, I want to try those different algorithms and figure out which one gives me the best score. For that, we use a method called grid search CV. For grid search CV also, I have a separate tutorial, and I'm going to link the tutorial in this video at top right corner as well as in video description. That's a very good API that sklearn provides, which can run your model on different regressors and different parameters, and it can tell you the best score. So let's import grid search CV. Other than linear regression, of course, I want to try lasso and decision tree regression. For grid search CV, I'm going to write a function. So this is how a function is going to look like. So I'll say, okay, find my best model using grid search CV. I will supply x and y as an input, and this should tell me which algorithm is the best. Okay, now in this configuration, I have specified the algorithm as well as the parameters. So grid search CV will not only do the best algorithm selection, for that particular algorithm, it will also tell you the best parameter. This is called hyperparameter tuning. To save some time, of course, I'm just copying and pasting the code. So scores, I'm going to store in this course list. I have this cross validation shuffle split, which will just randomly shuffle my sample so that I can get more better result. And then what I'm doing is I'm going through this Python dictionary. This is just a dictionary. I'm just going through that and initializing grid search CV object with this model as well as these parameters. Okay, this is the parameter grid that it will use. For cross validation, of course, I'm using the CV object with 5-fold cross validation. And then I will call a fit method. Once this method is called, I will append the scores into the scores list. Okay, and this gs.base score and base parameters will tell me the best parameters and base score for that particular run. Okay, and then I will return the resultant scores into a data frame. All right, so once I have this method defined, I can call the method on my x and y. I paused my video because the training might take some time depending upon your computer, but after running the training for some time, it came up with the best score. So here you can see that the winner is linear regression. It has the maximum score. You see lasso has 68%, decision tree has 72%. And for linear regression, these are the best parameters, which is normalized false. So I can conclude that my linear regression model is the best one. So whatever LR-CLF classifier I have created here, I will just use that. And it is already trained with 84% score. So I'm just going to use that to make property price prediction for a couple of samples just to kind of test it out. And for that, I will write a predict price function. Okay, so let me write that function. So the predict price function takes location, square foot, bath, and BHK as an input, and it will return you the price, estimated price. Now in your X array, the zeroth column, the first column is square foot, the second one is bath, third one is BHK, and for location, you know we have some 240 location columns. So for location, I'm locating the appropriate column. So let me just show you. For example, if you do x.columns, you find all of these columns. Okay. If I want to know the location of the second phase judicial layout, then I can simply do this here. I can say my location is second phase judicial layout, And when you run it, it gives you the column index as 5. You can see that this is 0, 1, 2, 3, 4, 5. Okay, so that's how this method works internally. And once you have location index, you can set that particular index value to be 1 here. And that's exactly what I'm doing. And by doing this, this will give you the predicted price. So let's execute this. And now let's make a price prediction for first phase JP Nagar, where the property square foot area is 1000 square foot, is 2-bedroom and 2-bathroom apartment. So you get 83 lakh rupees as an estimated price. And if the same thing is, let's say 3-bedroom, 3-bath, then you get 86 lakh, which kind of makes sense, you know. Let's look at some other location, some high price location. We know Indira Nagar in Bangalore is a little costly. So when you run this, you get, so in first phase JP Nagar, the price will be 83 lakh versus Indira Nagar is 1 crore 81 lakh rupees. And the same home for 3-bedroom, 3-bath is 184 lakh. Now, one observation you will make here is, so second column, third column is bath, the fourth one is BHK. So let's say for the same bath, and if I have more BHK and if I run this, I'm getting a little less price. You see 83 versus 81. You would think that the price should be higher if my BHK goes higher, okay? But that's not what our data is telling us. If you look at our data, we have many samples where for a given location, 3-bedroom apartments for same like square foot area, they cost less compared to 2-bedroom apartment. Now there could be different reasons. Like sometimes if you're 1000 square foot home and 2-bedroom apartment, then the size of each bedroom will be big enough. Versus if you're 3-bedroom, you're getting 3-bedroom, but each of the bedrooms are very small and compact, so someone might not like that. That's one reason. Other reason is because of our data is distributed. Sometimes we don't have enough information on why 3-bedroom apartments would cost less compared to 2. For example, check this. Here in Rajajinagar, I have 2-bedroom and 3-bedroom apartment. And the square foot is a little higher, but look at the price. Price of 2-bedroom apartment is 42 lakh more than this one. And if you observe our data properly, you will find many such examples. And that's the reason why the model is giving this behavior. All right, now it is the time to export the model to a pickle file. At the start of this tutorial series, we said that we will export this model to a pickle file, and then it will be used by our Python Flask server. So now that our model building procedure is done, we are exporting all the artifacts which are needed by our Python Flask server to different files. Okay. So as a data scientist, you worked with your business manager, you went through various iterations, you tried different models, grid search, CVK, full cross validation, you cleaned your data, you removed outliers, and you came up with this awesome model which is ready to be used in production. In real life, people also use A/B testing just to test a previous model versus this new model, but we're not going to cover A/B testing, etc. We will just look into how to export this model and then use it on our website. For exporting the model, also I have a separate tutorial, but it is very simple code actually. What you do is you import a pickle file, and then you just say pickle.dump on, and then you pass your model, your classifier as an argument. And when you execute this, it will export this file. When I open my directory, I see that I have this file, you see.
So Katie, you told everybody about training and test sets, and I hope people exercise it quite a bit. Is that correct?
Yes, that's right.
So now I'm going to talk about something that slightly generalizes this, called cross-validation. And to get into cross-validation, let's first talk about problems with splitting a data set into training and testing data. Suppose this is your data. By doing what Katie told you, you now have to say what fraction of data is testing and what is training. And the dilemma you're running into is you'd like to maximize both of the sets. You want to have as many data points in the training set to get the best learning results. And you want a maximum number of data items in your test set to get the best validation. But obviously there's an inherent trade-off here, which is every data point you take out of the training set into the test set is lost for the training set. So where do we set this trade-off? And this is where cross-validation comes into the picture. The basic idea is that you partition your data set into k bins of equal size. So for example, if you have 200 data points and you have 10 bins, very quickly, what's the number of data points per bin? Quite obviously it's 20. So you have 20 data points in each of the 10 bins. So here's the picture. Whereas in the work that Katie showed you, you just take one of those bins as a testing bin and the other one as a training bin. In k-fold cross-validation, you run k separate learning experiments. In each of those, you pick one of those k subsets as your testing set. The remaining k-1 bins are put together into the training set. Then you train your machine learning algorithm, and just like before, you test the performance on the testing set. The key thing in cross-validation is you run this multiple times, in this case 10 times, and then you average the 10 different testing set performances for the 10 different holdout sets. So you average the test results from those k experiments. So obviously this takes more compute time because you now have to run k separate learning experiments, but the assessment of your learning algorithm will be more accurate. And in a way, you've kind of used all your data for training and all your data for testing, which is kind of cool. So you just ask one question. Suppose you have a choice to do the static train test methodology that Kay told you about, or you do, say, 10-fold cross-validation, CV. And you really care about minimizing training time, minimize runtime after training, using your machine learning algorithm to output past the training time, and maximize accuracy. In each of these three situations, you might pick either train test or 10-fold cross-validation. Give me your best guess, which one would you pick? So for each minimum training time, pick one of the two over here on the right side. These three situations, you might pick either train test or 10-fold cross-validation. In a way, you've kind of used all your data for training and all your data for testing, which is kind of cool. So you just ask one question. Suppose you have a choice to do the static train test methodology that Kay told you about, or you do, say, 10-fold cross-validation, CV. And you really care about minimizing training time, minimize runtime after training, using your machine learning algorithm to output past the training time, and maximize accuracy. In each of these three situations, you might pick either train test or 10-fold cross-validation. Give me your best guess, which one would
Hyperparameters are the parameters of the model that are not learned during the training process, but are set by the user before the training. They are configuration settings that control the learning process and model behavior. For example, the maximum depth to allow the decision tree to grow, number of hidden layers and nodes in neural networks, or the number of nearest neighbors to consider in the k-nearest neighbors algorithm. The choice of hyperparameters can significantly impact model performance, as they help balance the trade-off between overfitting and underfitting. Let's see an example. In the KNN algorithm, the class of an observation is predicted by looking at the classes of its k nearest neighbors and performing a majority vote. The value of k is a hyperparameter that can be tuned, and it is often chosen to be an odd number to avoid ties. Intuitively, increasing k means considering more neighbors, which can lead to underfitting. Conversely, decreasing k may lead to overfitting. I trained 3 models with different k to show how important the k hyperparameter is in training the algorithm. Often you won't just have one hyperparameter to tune, but many. So, how do you find the best set of hyperparameters for your dataset? While hyperparameters are typically configured based on the dataset's characteristics, it's impossible to know the optimal set by simply examining the data. A straightforward approach to finding a good set of hyperparameters is to choose several potential values for each hyperparameter and train separate models for every combination. Then, you can use the validation data to determine which combination results in the highest score. Sometimes you'll notice that the best scores tend to be near the highest or lowest value of a given hyperparameter range. In these cases, you can refine the search by adjusting the range slightly while keeping other hyperparameters fixed. This process is called grid search. You create a grid of hyperparameters and search for the combination that produces the highest validation score. However, one major downside of grid search is that it can be computationally expensive, especially when training complex models on large datasets. Having 5 hyperparameters with 6 options, you will need to train the model 6 to the power of 5 times, which is equal to this number. Imagine the computational effort required. To be more efficient, we can do a randomized search. Instead of evaluating all possible combinations of hyperparameters, you define a range for each hyperparameter and specify how many models you want to train. The method then randomly samples from each hyperparameter range. This approach is more efficient, but it introduces randomization, which can either help you find the optimal hyperparameter set more easily or take longer. The effectiveness depends on the luck of the sampling and whether the specified intervals include the best set. As a rule of thumb, regular grid search is more suitable when you have a small number of hyperparameters with narrow ranges and when you are training a relatively simple model. Randomized search is used with many hyperparameters, broad ranges, and complex models. For large neural network models where training each model takes several days, the process becomes more complex. Different methods are designed to find a better set of hyperparameters in such scenarios. If you want to learn more about artificial intelligence,
In this video, we are going to cover in this video. Let's say you are trying to classify sklearn's iris flower dataset, where based on the petal and sepal width and length, you're trying to predict what type of flower it is. Now, the first question that arises is which model should I use? There are so many to choose from. And let's say you figured out that SVM is the model I want to use. The problem doesn't end there. Now you have hyperparameters. What kind of kernel and C and gamma values should I be using? There are just so many values to choose from. The process of choosing the optimal parameter is called hypertuning. In my Jupyter notebook, I have loaded iris flower dataset here, and it is being shown in a table format. The traditional approach that we can take to solve this problem is we use train test split method to split our dataset into training and test dataset. Here I'm using 70-30 partition. And then let's say we first try SVM model. Okay, so first I'm going to show you how to do hyperparameter tuning, and then we'll look into how to choose the model. So just assume that you are going to use SVM model, and using SVM model, you can train the model and you can calculate the score. Okay, here I randomly initialize these parameters. I don't know what is the best parameter, so I'm just going with some value. The issue here is that based on your train and test set, the score might vary. Right now my score is 95%, but if I execute this again, X train, X test samples are going to change. So it will change from 95 to now change to 1. I cannot rely on this method because the score is changing based on my samples. For that reason, we use k-fold cross-validation. I have a video on k-fold cross-validation, so if you want to pause here and take a detailed look at it, you can go there. But I will just give you an overview. As shown in the diagram, what we do in a k-fold cross-validation is we divide our data samples into n number of folds. Here I'm showing 5 folds. And we take 5 iterations. In each iteration, 1 fold is test set, remaining our training set. We find the score for that iteration, and we take these individual scores from each iteration and we make an average. This approach works very well because you are going across all the samples, okay? And we have a method called cross-val score, which can tell you the score of each iteration. Here what I have done is tried cross-val score for 5-fold, so CV is equal to 5 means 5-fold, and tried this method on different values of kernels and C. Okay, so here kernel is linear, here it is RBF, C10, and here C is 20. For each of these combinations, I found the scores. So these are like 5, you can see there are 5 values here, and these are the scores from 5 iterations. You can take the average of these and find out what is your average score, and based on that, you can determine the optimal value for these parameters. But you can see that this method is very manual and repetitive because there are so many values you can supply as a combination of kernel and C, right? C could be 1, 2, 3, 100. So for how many times you're going to write this line? So the other approach you can take is you can just run a for loop. Okay, so I'm doing the exact same thing but using a for loop. So I have my possible values of kernel and then C, and then I ran a for loop on both of this, and I'm supplying those values here. You can say C here, K-val and C-val, and then find the average scores, right? When I execute this, I get these scores. Okay, so with RBF in 1, the score is this, RBF in 10, the score is this, and so on. Just by looking at the values, I can say that RBF 1 and the value of C being either 1 or 10, or linear kernel and C being 1 will give me the base score. You can see that these scores are low. So this way I can find out the optimal score using the hyperparameter tuning. But you can see that this approach also has some issues, which is if I have 4 parameters, for example, then I have to run like 4 loops and it will be too many iterations and it's just not convenient. Luckily, sklearn provides an API called grid search CV, which will do the exact same thing. Okay, so grid search CV is going to do exact same thing as shown in this code here in line number 14. All right, so I'm going to do the same thing, but you will not that we will be able to do that in a single line of code. Okay, so the first thing you do is you import grid search CV from sklearn model selection, and then we will define our classifier. The classifier is going to be grid search CV, where the first thing is your model. Okay, my model is svm.svc. I'm supplying gamma value to be auto. If you want gamma to be in your parameters, you can do that. Okay, but for this example, I'm just keeping it static. Now the second parameter is very important. Second parameter is your parameter grid. Okay, in parameter grid, you will say, I want the value of C to be 1, 10, and 20. Okay, these are like different values that you want to try. The second parameter is kernel, and you want to try the kernel, and you want the value of your kernel to be RBF and linear. Okay, so these are the two values. There are other parameters in grid search CV. For example, how many cross validations you want to run. Grid search CV is still using cross validation. Okay, it's just that we are making this particular code block convenient and we are writing the same thing in one line of code. Okay, so CV is this. There is another value called return train score. This is some parameter that this method returns, which we don't need. That's why we are saying, okay, it is false. Once this is done, you will do model training by saying iris.data and iris.target. Okay, and once that is done, we will print the cross validation results. When you execute this, you get these results. Now, if you look at these results, you will notice that you got this mean test score. CV results are not easy to view, but luckily, sklearn provides a way to download these results into a data frame. Here I have sklearn documentation, and it says that this can be imported into pandas data frame. So that's the next thing I'm going to do. And all you guys are, I think, experts into pandas by now. So you just create pandas data frame and supply CV results as an input. And when I run this, I get this nice tabular view. Here you can see that these are the C parameter values and kernel values, and these are the scores from each individual split. Okay, we ran 5-fold cross validation. That's why you get split 0 to split 4, and then you have mean test score as well. Some of these columns in this grid might not be useful, so I'm going to trim it down and just look at parameter values and mean score. So you can see that these are the possible values of parameter C and then kernel, and these are the scores I got. Based on this, I can say that I can supply first 3 values into my parameters to get the best performance. So we already did hyper tuning of these parameters. You see that this how this works, right? And now you can have many parameters. All you have to do is supply them in parameter grid, and this grid search CV will do permutation and combination of each of these parameters using k-fold cross validation, and it will show you all the results in this nice pandas data frame. I can do dir on my classifier and see what other properties this object has, and I see some of the properties such as based estimator, based params, and based score. So let me try based score first. So clf the dot based score, and in the base score it is saying 0.98, which is valid. See, 0.98 is the base score. I can also do clf.best params, and it will tell me the best parameters. In our case, there are multiple parameters which gives you optimal performance, but you can see the point. You just run grid search CV and then call based params to find out the base parameters. And these are the parameters you're going to use for your model. One issue that can happen with grid search CV is the computation cost. Our data set right now is very limited, but just imagine you have millions of data points into your data set. And then for parameters, you have so many values. Right now, C values, I randomly took them to be 1 to 10. But what if I just want to try range, let's say number 1 to 50, okay? Then my computation cost will go very high because this will literally try permutation and combination for every value in each of these parameters. To tackle this computation problem, sklearn library comes up with another class called randomized search CV. Randomized search CV will not try every single permutation and combination of parameters, but it will try a random combination of these parameter values. And you can choose what those iteration could be. So let me just show you how that works. Here I imported randomized search CV class from the sklearn model selection. And the API kind of looks same as grid search CV. I supplied my parameter grid, my cross validation value, which is again 5-fold cross validation. And the most interesting parameter here is an iteration. I want to try only 2 combinations. Okay, here we tried total 6. You see 0 to 5. So here it will try only 2 combinations, and then we'll call fit method, and then we'll download the results into data frame. When I run this, you can see that it randomly tried C value to be 1 and 10, and then kernel value to be linear and RBF. When I run this again, it changed the value of C to be 20 and 10. This way, it just randomly tries the values of C and kernel, and it gives you the base score. This works well in practical life because if you don't have too much computation power, then you just want to try random values of parameters and just go with whatever comes out to be the best. All right, we looked into hyperparameter tuning. Now I want to show you how do you choose a based model for your given problem. For our iris dataset, I'm going to try these 2 classifiers, okay, SVM, random forest, and the logistic regression. And I want to figure out which one gives me the best performance. You have to define your parameter grid, and I'm just defining them as a simple JSON object or simple Python dictionary, where I'm saying I want to try SVM model with these parameters, random forest with these other parameters. I want the tree value of random forest to be 1, 5, and 10. And this n estimator is an argument in random forest classifier, okay? Similarly, the value C is an argument or a parameter in logistic regression classifier. Once I have initialized this dictionary, I can write a simple for loop. So I'm just going to show you that for loop here. And this for loop is doing nothing, but it's just going through this dictionary values. And for each of the values, it will use grid search CV. So you can see that the grid search CV, the first argument is the classifier, which is your model. So here you can see the model is classifier. So it is trying each of these classifiers one by one with the corresponding parameter grid that I have specified in this dictionary. You can see that parameter is the second object, second argument. And then cross validation is 5. I then run my training and then append the scores into this scores list. When I run this, my scores list has all those values, and all I'm going to do now is convert those results into pandas data frame. When I do that, I see a nice table view which is telling me that for SVM model, I'm going to get 98% score, random forest is giving me 96, and logistic regression is giving a little more than 96. So here I have my conclusion that the best 96 view, convert those, my score, run to the second object. Second, you see the model is classifier. So it is trying each of these classifiers one by one with the corresponding parameter grid that I have specified in this dictionary. You can see that parameter is the second object, second argument. And then cross validation is 5. I then run my training and then append the scores into this scores list. When I run this, my scores list has all those values, and all I'm going to do now is convert those results into pandas data frame. When I do that, I see a nice table view which is telling me that for SVM model, I'm going to get 98% score, random forest is giving me 96, and logistic regression is giving a little more than 96. So here I have my conclusion that the best model for my iris dataset problem is SVM. It will give me 98% score with these parameters. So not only we did hyperparameter tuning, but we also selected the best model. Here I have used only 3 models for the demonstration. You can use 100 models, for example, here. Okay, so this is more like trial and error approach, but in practical life, this works really well, and this is what people use to figure out the best model and the best parameters. Now comes the most interesting part of my tutorial, which is the exercise. You have to do this exercise, guys. Just by watching video, you are not going to learn anything. So please move your butt. Work on this exercise. Here we are going to take sklearn's handwritten digits dataset and then classify those digits using the listed classifiers. And also you're going to find out the best parameters for it. Post your answer as a video comment below, and if you want In last tutorial, cross validation on it. Are first block Jayana